The political spectrum runs from left to right. In a two-party system, politicians and media put a lot of effort into making you believe that you have to be either all the way at one end or all the way at the other. This isn't true, of course, and we will flesh out a mathematical argument for why the spectrum is actually quite useless and even dangerous, even if we add shaded colors in the middle to avoid polarization. We will also talk about shoe sizes and about bouncing marbles. Underneath all of these diverse topics is a pattern so common in statistics that you've undoubtedly seen it before: the Gauss curve. In order to understand such a curve, we have to count the number of paths that run from home to the pizza restaurant on a two-dimensional grid. At each point on the grid, you're only allowed to go down, and you have to decide between going down left or down right. How many ways are there to get from the starting point to itself? Just one, of course, so we put a 1 right here. At the next level, there's only one path that leads here, and only one that leads here. So far, so boring. Now, at the next level down, something interesting happens. We have two distinct ways of getting from home to the middle point. We can either go left-right or right-left. So we should put a 2 here. The positions at the edges can still only be reached in a single way. How many paths lead to this point? Well, we can either come from the left or from the right. In order to come from the left, we first have to get here, and we already found two ways of doing that. If we want to come from the right instead, we first have to make it from home to this point, and we already know that there's only one way to make that happen. This sums up to a total of 3 possible paths. You can easily fill in the rest of the table. The points at the edges of the triangle can always be reached in precisely one way. Either you take a left at each turn, or you take a right at each turn. For other points between them, you add up the number of paths that lead to its top left, plus the number of paths that lead to its top right. Each number is the sum of the two numbers above it. The resulting table is known as the Pascal triangle. This number triangle has too many cool properties to go into here. I'll just mention the ones that are relevant for our discussion about shoe sizes and democracy. First, I'm sure you've noticed that the table is symmetric. Intuitively, that's because the entire setup is symmetric. At each crossroads, you can either go left or right, and there's no built-in preference for either. The numbers in each row keep getting larger as we move towards the middle, and then they drop down again. You might say that the values form a kind of mountain with its peak exactly in the middle of the row. To get a good feeling for the precise shape of this mountain, let's plot the values on a diagram. The second row gives us a small triangle because the position in the middle can be reached in 2 different ways. On the next row, we get a small molehill. As we go down to wider rows containing larger values, the molehill keeps growing, and you clearly see the familiar shape of a Gauss curve emerging from the fog. Why, though? Why is this well-known bell-shaped curve hiding in these path-counting numbers? I mean, in real life, Gauss curves are the result of measuring people's heights and shoe sizes. This grid of paths meandering left and right has nothing to do with shoe sizes, does it? Well, let's see. The size of your feet depends on many different factors. Some of those factors are genetic. Others are environmental, such as your diet or the availability of healthcare. Each of those factors could either lead to smaller feet or to larger ones. And when we add up all of those influences, the end result is your shoe size. I find it very instructive to visualize this with a marble falling down a triangular set of pins. At each of the pins, the marble randomly chooses to go to the left or to the right. So this first pin could represent a specific genetic factor, and it either nudges your body to produce slightly smaller feet or slightly larger ones. The marble lands on the next row of pins, which decides on some other genetic factor. The next row after that might give another small nudge based on your diet, and so on. On the way down, the marble adds up all of those little decisions, and it lands in one of the bins at the bottom, where you get your final shoe size. If we repeat this process with many more marbles, each marble, each person, follows his or her own unique trajectory down the triangle of pins, and we all land in a specific bin at the end. The Gauss curve is simply the result of adding up large numbers of independent binary choices. This explains the relation between path counting and statistics. I love this visualization because it says so much about where Gauss curves come from and how you should read them. On the horizontal axis is the shoe size, and on the vertical we have people. Each marble is a person. On average, all those little binary left-right decisions have a tendency to cancel each other out. That's why there are many more marbles in the middle than at the edges. There are many paths that lead from the start to the moderate bins near the middle. There's only a single path to each of the extreme bins. Now back to the Pascal triangle. There's an easy formula that gives you the value for any number. Instead of counting up all the different paths, we can just calculate this fraction of factorials. These expressions are often written like this and pronounced n choose k. If you have 7 objects and you have to pick 3 of them, you can do so in 35 different ways. Say there's an election in your country, and you get to vote for one of 2 parties, blue or red. There are many important questions and issues and policy proposals. On each of those proposals, you can decide between left and right. In a healthy democracy, your answer to any of these questions should be completely independent from the answer to any other question. So maybe on the first policy issue, you are in favor of the blue proposal. But on the next question, you find yourself preferring the red approach. This is an important detail if we want to explain where the Gauss curve comes from. The binary decisions that you make on your way down have to be completely independent of each other. Now, what is the connection with n choose k? N is the total number of questions, and k tells you how many times you went left. Out of the n total questions, you answered k of them to the left, so you picked k left turns out of n possible turns. You chose k out of n. This should give you another clue for why the rows are symmetric. If you focus on right turns instead of left ones, k now tells you how many right turns you took. You end up at the horizontally mirrored position, but the total number of paths that could lead there is the same. You can also find the same symmetry in the expression with the factorials. When switching from one position to its mirror, we change the number of left turns from k into n minus k. This just gives exactly the same expression. Look at the sums of all the numbers on row n. Do you notice anything? They are all powers of 2. Can you explain why this happens? Share your best explanation in the comments, and on your way there, take a second to hit the like button and to subscribe to the channel if you haven't already. Thanks. The fact that the total number of paths doubles on each row tells us that the political landscape is huge. It means that if your political opinions really are independent, there's a vast number of combinations of opinions you can hold. The place where you happen to land on the political spectrum the bin that your marble ends up in, is merely a sum or average of all those choices. By taking this average, we completely lose the subtlety and diversity of the path that you took on your way down. This is why I want to argue that the political spectrum is a poor representation of people's true opinions. We go much deeper into this in a companion video where we focus more on the implications for society than on the actual math. The main goal of our channel is to make higher math and physics more accessible for a large audience of people who are not necessarily experts in these topics. Our videos take a lot of time and effort to produce, and our financial buffer is extremely limited, so it's important that we ask for your support. You can easily give our channel more visibility with a thumbs up or a comment below, or by sharing this video on your social media channels. That way your friends and family can also learn about the Pascal triangle and its connection to Gauss curves and political polarization. If you have a few bucks to spare, you can set up an account on Patreon, where you'll get to watch our videos many months in advance. And we also occasionally publish exclusive content on Patreon that never makes it to YouTube. We are very grateful for any help you can give us.